step. So the first thing is to agree all together. So to agree from the scientific point of view, and also for requesting the funding to be able to have a new accelerator. So remember, I'm talking about accelerators, but the process of having the experiments approved is a parallel process, so it's not a separated one. It will be completely useless to have an accelerator without experiments to explode it. So as I said, we need a strategy, something that put us together. So the strategies are prepared following what we call a consultative process, means all us together. There are global meetings with the community, sometimes in the labs, sometimes it is a real global gathering, like was in the past in Poland in 2013, or after in 2018 in Granada, where all the community has discussions, presentations, is what we call town hall. And there's also after close meetings among the panel, because there's a panel of experts, not only from that nation, but really representing all the community, that will write a final report. The strategies are updated regularly and are not limited to the States and to Europe. There's also the ones, is the equivalent ones in Japan. And of course, there's also in other parallel fields. So there's also, for example, a strategy for astroparticle physics. In the slides, you will see that I have put all the links so that you can consult them. The one of Europe and the States in the past were more or less in parallel. Not only the COVID influenced this preparation of the meetings, what makes that today we had the European strategy that was decided in 2020, just before really the COVID struck us, while the strategy from the States, it's now in preparation. So it's really the hot moment for the preparation of the new strategy for the States. Next slide. So what appears in all these documents? So is what we call drivers. So the ones that you have in front of you are the ones of 2013 that was created for the States, for the United States. In general, the reports are giving what we call work axis. So it's not something very concrete. They give you an idea of what is the important thing. So if you look at the slides, Higgs boson, neutrino mass, dark matter, cosmic acceleration, explore of the unknown. So, and there was also a point in education. So they are giving you some guidance. As I said before, normally before we're nearly in parallel. What is not the case. So we are really curious of what's going to be the result of the new P5 in the States. Every strategy takes in consideration what the others have as main drivers. I call it cooperation, means that it's a mix of cooperation and competition. We don't have anymore in between the two sides of the Atlantic, the same kind of competition that we had in the past. You remember the slides where we had UK had a machine, and then the States have a machine, and then some have a machine, and then something in the States were another machine. Probably the only one where we have a kind of competition still is with China, that have also an equivalent of, you will see, of FCC. But now it's really cooperation, a little competition, but real cooperation. So in all the strategies, consider what the other strategy have put, not to kill among themselves, not to, and really cooperate. So the 5 points were after taken by each laboratory and put as a strategy of where they were going to put the efforts. The slides come from 2014, and the blue is for construction and green for operation. So if you look at the dates, you will see that, of course, the ideas that they had in 2014 did not become reality. So if you look like there, HLADC have to start 2025. Now it's 2029, and the same nearly with all the experiments. So they also divided in 3 axes. One, it was the large project in the States, MONG2, MON to electron conversion, and Fermilab, the long baseline neutrino facility in North Dakota. So big experiments and big machines in the States, after a part of cooperation, and really put it stated that really they wanted to cooperate with an ELC. It was going to be done in Japan, and clearly with high luminosity, not only from the part of the experiment, but also from the part of the machine, where we have a very, very strong collaboration with the states. It also contained medium and small projects that for them were key, since the kind of thing that don't require a lot of money and resources, but that can give a great discovery. So you have the Large Synoptic Survey Telescope, the Dark Energy Spectrometer instrument. I always have problems to remember what is this ILSSFT. So you will have it also in the slides. The microwave background experiment. So all kind of small experiments, and of course all the tests for the short-base neutrino experiment. So to preparation of when they will have the baseline neutrino in North Dakota. So all these were, and some of them have advanced very well. Others have also have some delays because COVID have affected nearly every laboratory. We can say that less or more, but has clearly affected your priorities and the funding. Come back to Europe, where we had this strategy created already in 2020. As I said before, all them, they have big considerations. So if I read, for example, one of the sentences was, an electron-positron Higgs factory is in the highest priority next collider. So after each laboratory and all together, we decide what it means. It means that, yes, we will need a Higgs factory. It's not decided if it's going to be LC, if it's going to be click, or if it's going to be FCC with electrons and positrons. What it says is that we have to work together to make the reality of this to happen. It also gives long sentence like, for the longer term, the European particle physics community has the ambition to operate a proton-proton collider at the highest achievement energy. In some way, it's saying that, yes, we expect, we dream, we think that we have to go in the direction to be able to have what today in Europe is the FCC with hadrons. It not says, I need FCC. It needs, I will need to work so that I can develop it, and something equivalent exists in the long term. You will, in the sentence of the strategy in the state, you see that the sentence was 10 years and 20 years. I will say that this is even not enough. All the strategies really go really beyond 20 years. Some of them even give hints of things that have to happen in 50 years. And if you will see, when we will see the FCC slides, the hadron machine now it's foreseen for 2070. So it's really far away. Another sentence that are not talking about which are the machines, but the technologies that we will need. If I go deeper, and this slide comes from the Director General, so how the strategy was presented to us, they will go deeper on this interpretation of the point. So effectively, our Director General not only state that we have to work in R&D, but also stated directly to realize a machine of the energy frontier, high-field magnets with at least 60 Tesla are mandatory. So she really wrote it down, so to say, it's not anymore that we have to make R&D. I put you already a milestone. I put you already an objective. I want a magnet that works, exists in Tesla. And we will put all the resources for that. Because remember, it's not only objective, it's also the resources that go with it, the personnel that have to go with it. And the same thing for all the different points. Up to the level of my group, we have received several tens of millions used to make the investigations for the tunnel, for FCC. So it's not anymore on the paper. We are really moving to really concrete things that can be done and can demonstrate the feasibility of some of these dreams. Sometimes even go even further. So it's not only what we have to do for making these accelerators that we think are the roll down of those recommendations, but we also go beyond our laboratories. That means that, again, we are not anymore alone. It's not only CERN that decides, it has never been, but it's really all the community together. So you will see in high luminosity, we work with more than 40 laboratories together. We can never it's impossible to dream of making an accelerator like that alone. So always we will have to cooperate, always we have to find what is each one of us going to do. And again, be making synergies all the time. So the translation that our Director General gave to us also put some points on other things that are not there, but we don't have to forget, because maybe are the solutions. I will in a certain moment explain you that you always have to have a plan A, B, C, and even D. So that is probably why she also put us that, okay, but still we are going to work in plasma physics so that we have a new generation of the weight accelerator, muon colliders, energy recoverers, Linux. We have to think on how we reduce the energy consumption of our machines, because we know that in the future we cannot continue consuming 1/3 of the energy of the Canton of Geneva. We have really to operate with less energy, so that use less energy to operate at a higher energy. So all these things were also put together. So it's not use and simple, I want an accelerator and I put you these objectives. The strategy, as I said, goes beyond I want a new accelerator. So it also points on theoretical research, what is the R&D program for the detectors, software and computing, but also things on culture and outreach. So it's really more global. And again, in the slides, you have all the reference so that you can look and which was the European strategy with also the explanations. So in the strategy, and I know that looks like forget, it's true. It talks about the future, even the future in 50 years, but also talks about today. And one of the objectives that was clear is that we have now an accelerator that is LHC, and it must work, and it must give us as much discoveries as possible while it will be running. And of course, this is translated by two things. One is HL, so the future high luminosity collider, so the upgrade of LHC, but also the full exploitation of our present machine. I know that some people, when in 10 years ago, we were defining the concept of high luminosity, the people said, you know, if we avoid the 3 years that you will need for all this upgrade, we will run the machine with higher, but not so high luminosity, and still we will have the same integrated luminosity. It's not true. Okay, there you will see why HL, and we have already said why HL is needed. But that implies that we really have to continue upgrading not only LHC, but also all the injection chain. And this is already done. So this is what we did in LS2. So in the last launch done. So all the machine now is really upgrade, all the injection chain is upgrade, so that we also contribute to the future luminosity of high luminosity. So it's again, the strategies are present, near present, or near future, and real future. Now, before I start with high luminosity, I want to put some slides of I will say, a nugget of my knowledge, since it's not so simple. I know that when people make an accelerator, and I have really good friends that they make you an accelerator on paper and they look great, they forget how hard and how long it is to make an accelerator. That is the scale of LHC. People really, again, forget that LEP was done in 89, so inaugurated in 89. And in 83, we had already the first concept of LHC. Okay, it was because they wanted to put LHC and LEP in the same tunnel, one over the other. It was because we had a competition with the States, and we had to demonstrate that we were able to make a better collider than them, or at least faster and cheaper. But look at all this data. All these dates and how long it takes, 83 to 2009. So, and people also forget, so which are all the steps? So if before you have an approval of a project, you need a conceptual design report. You need a first baseline. You need an RD map of the technologies with the feasibility studies that, and how you think that you will, all the steps you think you will need to get this technology working. You need a list of potential collaboration and in-kind contributions, because if you are alone, you will never build anything. So who is with you? Who are your partners? You need a schedule with resources, and you will have thousands of reviews that will look if really you can do it, and you will, don't repeat it, lie, so that the cost is affordable. And of course, after it will be constant, there will be some discussions about why you had put a lower cost, because always people forget. Remember again, people normally had a clear idea of how much it costs the accelerator, but normally forget all the things that go around: transport, installation, commissioning, ventilation, cooling, cryogenics. So all the things that go around. And even with that, you will still need a preliminary design, technical design report. And only with that, maybe you get approved. But even if you have, for doing all these things, normally, as you are a non-approved program or project, you have little resources. So it takes even more time. And after that, you will still need to really make feasibility, not any more studies, but really feasibility of the components. So you have your models, your prototypes, and you will have to go to industry and beg industry to make what looks impossible. So, and you will have to split all the baseline in small work packages, and people and organizations, other labs will have to get the ownership of them. And after have to be integrated. And again, after you will have to build it. So it's a really long way. And I have listened to a lot of people telling, but it can be done faster. Maybe in the past, but not today. Here is the slide that normally we put to talk about the glorious years and how things evolve. But in the same way that there you have the glorious moment, I can tell you that I remember a lot of non-glorious moments. I remember testing the magnets in '96 and not having one single magnet that worked and reached the right magnetic field, not in any of the things, not as Doppler, but all the kind of multiples that should not have been there. But I remember also how we worked hard to make it work. I remember the problem of the cryogenic line and not being able to install it, and the council telling us that if we were not able to install the cryogenic line, well, we were going to be cut down. But at the end, we managed to redo completely the cryogenic line and manage it. We had the crisis of the DFVs, we had the crisis of the collimators, we have bankruptcy of different companies. We have to retake back beam screens, cryostating. So I know that I'm not discouraging anyone, because I had a lot of fun. Probably were the best years of my life, even if I had all kind of little histories in the tunnel. But again, it implies a lot of effort and a lot of collective effort and a lot of courage to get up when things go wrong. The satisfactory thing is that after things work, even if the machine was broken after 9 days and we have to repair, but I have never seen so much energy and desire of getting things correct that in the days after the incident. And yes, after all this long wait, we managed to have Halloumi. It's not Halloumi, LEC working, and in the future we'll have Halloumi. But again, remember, it's a long way. And a long way, well, there's things that comes from you, and there's also unpredictable events that come from outside, like COVID. These are pre-schedules where we said each one of them represents when we said that we were going to make the LS3 so that we install high luminosity. And some were delayed because of technical problems, some because of funding, and some because of COVID. So there's always a reason, and don't get discouraged. It happens. Every port accelerator has been sliding on time. Don't forget the industry. I have talked about bankruptcy, but you must always design with resilience. You must always have a plan A, B, C, and even D. I remember when we created the magnet facility, and people thought, why we are making a place where you can fabricate magnets, or when you can assemble cryostats. It was part of our plan B and C. Well, it came after the first failures, but it's important really to think further and be resilient and foreseeing all catastrophes that can happen and a way of solving it. And teamwork is key. It's key because always with a good team, you can solve nearly all problems. And finally, make outreach. And it looks like why. Nothing is more important than the stable funding and support from your countries. That makes possible that even when you destroy your accelerator after a few days, still they continue supporting you and paying their contributions. So it's important to demonstrate not only to your friends, but also to all the community, and in the most scientific possible way, that constructing all these machines and experiments, of course, gives a real return to the society. And this was one of the studies that we did with high luminosity data to demonstrate that FCC, even if it's going to be quite costly, it's worth. So next step, which type of accelerator? I put these slides because a lot of people discuss about which is the future accelerator. And you can ask yourself why people discuss so much if ELC or click or FCC, which type of FCC or another. It's because they put the first questions. First is fixed target collider. Well, at least this one probably is the only one that is easy to answer today. In the past, no, because if we have to think on fixed targets and colliders, both have given us a lot of Nobel Prizes. So there's 6 Nobel Prizes with fixed target and 6 with colliders and 4 with non-accelerators. So this is the main ones. There's all the other ones I have presented. So up to the 70s, both had enough energy to break great discoveries. Today, we really are exploring high energy frontiers. So it's only the colliders that can work. So that's why every one of the future accelerators are always colliders. After, you have to decide which kind of particles you are going to use. And there's a lot of discussion. Why? Because some of the physicists, they say, it's the moment to go to precision physics. Others that say, no, let's go for real discovery. And of course, it's not the same to use an electron that is pure than to use a proton that is a mix of things, a mix of quarks. So that's why we had these two communities, the one of pushing an ELC and click with electrons that wants to go with precision measurements. Was the same thing that happened between SPS and after the LEP. They had a discover machine and they said, and now is the moment to make precision measurements. And the other ones that say, no, we need a new smash machine. We need higher energy as possible. There's always also the discussion about circular and linear colliders. And I will make you a joke just to try to, I don't see you, so to try to make you smile. Every person that I know that loves magnets, always they say a circular collider. And everyone that I know that loves RF, they say a linear collider. It's not really true, since each one of them, of course, have their pros and their cons. For me, the bigger problem of the linear colliders is the single experiment. In a circular collider, you can have 4, you can have 7, you can have as many as you want. It's not true, but let's say that you can have a certain diversity. In a linear collider, you can only one element in the middle. So it's easier to have a community together when you have a circular collider, and then each one of them can decide, I do my CMS and you do your Atlas. And a smaller community says, and I look for this characteristic LCB, and I look for other characteristics plus ions, and then I go for ALICE. So it's easier to get a bigger community if you have the possibility of have several experiments installed. And finally, the energy that you are targeting. High energy physics is ambiguous. What means high? So it's clear that today we are looking at 2 types of machines. So the heat factories are high, but we are talking about 240, 250 gig electron volts, and the biggest masher machines. So the big colliders that will go to the energy frontier, and then we are talking about tens of electron volts. So of course, they both explore completely different things. They are looking at different physics, using different methods. And so that's why also we have different communities, each one supporting. There's people that is on both communities, but they are rare. Normally are more really divided, and there's points of in common. So it's there, and always I will say that are complementary. That's why the most reasonable ones is say first do an ELC small or so let's make an Higgs factory and after go for the energy frontier. The problem is that as we have an FCC with electrons that could work as a Higgs factory, then of course gets a real competition between Linux and circular colliders. So, and last, parameters, an experience for of machines, existing machines and available laboratories. It's again, too often we forget that we need other accelerators and we need a community. So it's always easier to make a new accelerator where already there are accelerators. That's why there's no new laboratories that appears from nowhere. Because at CERN, we use still the PS, SPS, of course, the Linux we have modified now and we have Linux 4, but the old Linux were working for more than 40 years. So, and we have a real strong community of technologists. So it's easier to make a new accelerator where already there are accelerators. So these are also an important parameter to take in consideration. China thinks that they can do nearly an accelerator from zero, and maybe they are able. I'm not denying this possibility, but it's clear that it's easier to make a new accelerator in Fermilab or at CERN than creating something from zero. So now that we have seen the perspective, let's go back and go to the future, but the near future. So what is tomorrow? What is going to happen? I will say tomorrow. So tomorrow, after the LEC, and as we know, in 2029, LEC in any case will be stopped by the effects of radiation in the tertiary regions. So we need a plan, and this plan was started in, well, it will depend. Some people will say 2012 because it's when we presented documents for the European Union to have funding for the first conceptual studies. Other people will say far before, because in reality, high luminosity started like, I want only to upgrade the triplets, and then it come to, but if I upgrade the triplets, why I don't improve all the machines? So even if we started so far away, the machine as high luminosity will only start operating in 2029. And high lumi had a lot of this concept of reduce, rethink, improve. So every technology that we think about it, we thought about, okay, can I use it for high lumi and can be useful for the future for another machine? Let's consider it not only an improvement of the machine, but also a technological project. One of the objectives that we had. So make R&D to the future accelerators. So as I said, there was another point. You remember that we say that FCC have to look at the feasibility, but also the feasibility as a global project. So high lumi also was a kind of test bench. So we said we cannot build these machines as alone. So can we have personnel from all around that works in high lumi and makes in-kind contributions? And so in French we say on a pris le bâton de pèlerin. So we take like making the long way to Santiago de Compostela to try to find other institutions that were willing to work in high lumi. And we were quite successful in the sense that, well, the experiments always is like that. For the machines we had in LSD use some contribution, very important contribution, but only certain contributions. And here really we obtain contributions from all these labs and even more today. I think that is not even the last one. So we create this first spirit of let's build an accelerator like it was an experiment with all in-kind contributions. But it's not the same way. When you make yourself your accelerator with industry, you are the owner of your delays. But when you're making collaboration, it's different. For example, you can imagine what was the impact of the 6 collaborations we had with Russia. 1 year ago. And then you have to again to think on plan B, C, and D. So it's not the same. Implies a complete different governance. And the accelerator is not anymore your baby. It's a baby of all of you. It has a lot of parents. So as I said, Hilumi was not only I replaced 1.2 kilometers of the LEC machine, was also I will try a lot of technologies. Some will be useful, some maybe not. But at least I try new technologies that could be used in the future. Of course, civil engineering is not, but it was considered as bench for if I have to make a 100-kilometer machine, how much is going to cost me and how difficult it's going to be. It's not fully true because the 100 kilometers machine will go in a more empty space, let's say, and it's far away and have a lot of more challenges. I can tell you, I know very well which are the challenges today of the civil engineering. But in the case of Hilumi, it was how I built an infrastructure so close to a machine that is working, and how much is going to cost really to make the galleries and the connections, and how much time is going to take. For FCC, we'll use other technologies because it's far away. You can have boring machines. It's a completely different structure, but at least gave us this first concept of how much is going to cost, how time, which are the interference, which are the problems. And the same for all the technologies that you have around, the superconducting links, the new materials for the collimators, the use of deflecting cavities, the new type of magnets with new materials, all were really technologies that we thought are important for Hilumi, but they are even more important for exploring new R&D for new accelerators. So I go fast for the new components. I have all the reference for the technical design report if you want to know more in detail about high luminosity. So, but one of the major challenges was the inner triplets. So the insertion regions, quadrupoles, and all the magnets that go after. So we are changing from the Q6 until, let's say, the experiments. So from the new triplets, we use a new technology with NeoRCT. Of course, some will not accept this statement. Probably what we have learned is that it's probably not the material of the future because it's so difficult to use it, and it's so little it's so difficult to pass it to the industry. It probably is not the material that we have to dream about for an FCC. What is a very interesting discovery, and is at least we know that there's a lot more work if we want to use, and that's probably why the FCC data with hadrons have moved so much in the last years, because we know that it's probably not the material and that we will need to really work a lot to have a material that will allow to have 16 Teslas or 20 Tesla magnets. But also we explore all kind of new magnets, and we increase also the capacity of other labs to make magnets. So if you see all these flags, it's because they are not done at CERN. So ENFN, CMAT in China, in Japan, in the United States, all them, they built up again this capacity of making magnets of all types, conventional, with completely different costed design, with kiss and bladders, and all kind of technologies that before we had not used it. And how to pass it in the industry. We had a lot of difficulties, but some of them are now built in the industry, fully in the industry. So we know that we will have this with us in the moment that we will pass to an FCC. We had a lot of work also for the crack cavities. They are not new, since crack cavities and deflecting cavities were already used in Japan. But the ones we create were really different because were built to be able to pass to the industry. And I insist a lot, we cannot dream in a new future accelerator if the components we are designing cannot go easily to the industry and can be repeated once and again and again and again with the assurance that one after the other will be the same. So the work on the cavities, that was one of the, again, the LEC spirit with deadlines all the time, were also with this capacity of I don't only want to make crab cavities, but I want also that the industry can do it in the future. Also because the industry of the superconducting cavities is now very small. There were some bankruptcy, so that is really important that we maintain the industry alive. The same thing for the collimators. We explore other materials. We explore new designs, industrializable designs. So that can be used again for future, not only for HL, but also for future accelerators. Or the superconducting links that I think that the main point is that, again, we work with industry and use magnesium diboride. People always say, it's high temperature. No, I will say it's higher temperature superconductors. But again, being able to pass it in the industry and to use it and develop it and that it works, it opens also a way for future developments. And developments also happen with power converters, again, for making it more, to have again the industry with us, to make it more standardized, to make it cheaper. Again, it's important key. Energy extraction, the click, a new technology again for energy extraction, develop it in the industry of all kind of myriad of beam instrumentation, new beam instrumentation. So to be sure again that are there and ready for a new accelerator. But also with ultra vacuum, where we work a lot on materials also for all the beam screens, with the idea of supporting higher levels of radiation, or with something that's, let's call as a traditional as transport. I know that looks fun, but I remember a presentation of an expert on transport that say, believe me, we are not Jedis. We cannot make levitation. And I know that maybe it makes you smile, but it's true. The most part of the people when design things don't think on which is the gravity center, and they don't consider that will have to be taken by someone and move to the position. So there was a lot of work also on how to transport all the new equipment with all the new challenge that we have. So with customized vehicles, forklifts, and guess it, all are more expensive than we thought. So whereas there's a lot of learning curve of on how much is really going to cost a new accelerator. This picture is used to give you the impression of how much we are going to change and how much is going to be installed in the new tunnel that we have created for high luminosity. And yes, everything that you have seen is new, fully new. And we will have a part of dismantling of the machine, remantling the machine, but in the meanwhile, we have all the work of populating all what we call double-decker, because it's a second level since a second parallel tunnel, with all the power converters, again, the RF capacity for being communicated to the RF cavities, and all the powering and cooling that is necessary, and a lot more. Two slides used to show you that it is a true collaboration. You see there the flags with each one of the components and where they come from. Okay, the ones with Russia now it's going to change, but used to give you real impression on how it's a really collaborative project, and anyone in the future will be like that, a fully and true collaboration. Without this, it would be impossible. And remember, 1.2 kilometers of machine, 18 years from the first concept to, I hope, commissioning and first beam. And it's only 1.2 kilometers. Now, the future. I hope you are still smiling and don't think that, my goodness, it's too complicated. Let's forget it. We will never have a future collider. I think every time has been like that. Every time we have need a lot of courageous people to start the adventure of a new collider or a new accelerator. So think on that, since maybe looks impossible. I suppose that when a shopper went to every country to say, I want to build a 27 kilometers lepton machine, call it Future Lab, everybody looked to him like it was impossible. But he did this. With Picasso, he did both together. And of course, all the other persons that work together, and of course, those that work in experiments. So even the most incredible things are possible if you believe on it. And today, you remember the scientific priorities for the future? they are there. So yes, they talk about LAC, they talk about Halumi, they talk about a Higgs factory, but they say, investigate this 100 kilometers collider. Dream. Dream, because only things can happen if you dream, and you dream far away. If you really look for maybe things that look impossible, but really are going to make a change. So what is the agenda for this new collider? So this is the one that you have seen there. And yes, it will take a lot of years. And the next 3 years are really important. In 25, we have to present this feasibility study, and we must look credible. You remember the steps? You have this concept, and after you go for mapping your resources and the schedule and making all this feasibility study, all the different components, or at least of the technology of the components. So 25 will be the key moment when we'll present the report, and then they will be taken for the new strategy that will say, yes, go ahead or not. Okay, so we are again in a new bubbly moment. You see things in different colors because there's parts that are for, I don't think you can see my mouse moving, but for the part of the future Hadron Collider. That yes, it's probably going for the 2070, but if we don't start working today, it will never happen. And you see there, now, I know that some people ask, why not to go for FCC high luminosity, it's a high luminosity, Hadron version directly. It's like a LEP and after LEC. It's a way of not having such a big gap between two machines. LEC with high luminosity will work until 2040, 41, but no more than that. If we don't have a machine just after, if we have a gap of 30 years between one machine and the other, I suppose that all you will leave the room, the equivalent ones in 2040, because it's there no machine, there's no discoveries, there are no experiments that are working, so there's no physics. So some of the justifications it's making 2 steps and make a physics that is really more continuous. It's a decision. It's a real decision. And again, I'm not going to be very politically correct, but of course, FCC with electrons and positrons is going to be a competitor of an ELC or a click or another machine that is going to be a Higgs factory. So it's also a proposal that it's in some way really competing and not cooperating, but competing with other solutions for Higgs factories. There's also, I put there that there's the China, which is CEPC, that it's an equivalent of, again, is a vulgarization, but it's really an equivalent of our FCC with electrons and after moving to hadrons. Maybe they do it before, and this will be a killing factor, because if they do it, then it will be difficult to justify that we have in both sides. Like it was difficult to justify 2 LHCs in both sides of the Atlantic. Which are the points for the feasibility study of the FCC? The ones I have put there. And you will see that not all are technical. We have for the first time put some points of sustainable operation. We really have clear in our mind that with the present energy consumption of high luminosity, we cannot imagine FCC, even if the first version with electrons will consume a lot less than the final version. We have also to consider this governance, this capacity of getting all together and create, like we have done for high luminosity. So how to create new machines with a really collaborative and a governance like the one of the experiments. So there's a lot more points that not just making a technical design report with all the components that will have the machine. And so the clock is ticking. So it's really 2025. So why I have put this this slide is because I had already pointed that we have to learn from our experience. Some people think on Accelerator and says, I will make everything new. And this could work, but I don't recommend it to. So FCC, if some people say is a deja vu, something already seen, it's because it's true. But I think in a very positive way. It's taking in consideration all the developments, all the things that have worked in the other accelerators and integrated inside. Because it's only combining successful ingredients that we will have a successful machine. There's use for your info, the parameters, and this is for your info, the layouts, with finally a 90.6 kilometers. I have had the pleasure of seeing all the nearly 100 variants that my team have prepared with all the problems, and I have people of my team now going all around France for the land permits to excavate and to make the first digging and the first French carottage. So it's a non-negligible, but really go-no-go part of the project. During the construction of LEP, they had a lot of problems when they were digging in the Jura site. We have to be sure that this machine can be done, and the civil engineering is not going to cost a lot more because of the difficulties on the ground excavation, and that we don't have the water infiltrations that can make it impossible. This machine, and a lot more concepts, I can tell you, a lot more than you think, and I have never thought in the past. And this is how it will look inside. We have a lot of integration drawings already, and I will always recommend in Halloumi everything was growing at the same time. So we have integration from the zero, and I think is vital for making a new accelerator. Not only to think on numbers, but really to integrate the components, because they have to fit together. And I know it makes you smile, but really they have to fit together. And I have seen too many times problems that should not be there, and it was just by lack of integration or by lack of understanding on the limits of civil engineering, for example. And I saw them in Atlas a lot. These are the parameters for the version with hadrons, and here the real challenge. And the real challenge is to find the technology that will allow us to have these 16 Tesla magnets produced in the industry. And I put this produce it in the industry because it's really, really different to make a magnet in your lab and test and repair and rebuild and put a lot of money because of the efforts of making it work, than produce it in industry, and that every week there's several magnets that have to go from the industry. Remember, it was less than around 3 years for the production of all the dipoles of the AC. Here is not 27 kilometers, it's 90 kilometers. So you need to really make things that are industrializable and really that every time it's the same magnet goes out. The future is not only that. I have put here a panorama, and also in the reference, you have a great article that looks at in detail of each one of the accelerators that appears in this panorama. You have also things on ion colliders that I haven't put there. You have not only ELC and CLIC and FCC and CEP, but you have also tau charm factories. You have other versions of energy frontier colliders that use LEC with other version. I remember high energy LEC that was very a real competitor of high luminosity in 2012. But we have also great ideas for muon colliders and concepts that maybe one day will make great things like plasma, even if today it's not for high energy physics. That is just to give you the general light collider, and that's why I point this concept of the weak point of a linear collider, this single.
Isabel,
yeah,
do it in
it's
5
4 minutes.
5 minutes?
Yeah.
Okay, thanks.
It's 7 minutes. You will see, even less. Okay. So this is used for your information. What is the plan for the CLIC implementation? Of course, each one of them, they had a short and a long version. So you have the small one and the big one. Why we have them? There's because, of course, it's a question of cost and resources. And always in a small version, it's less costly than a long version. But from my experience, and again, it's my own opinion, you don't put back again an industry to produce the same component 2 years after. The most part of them have dismantled all the equipment, all the tools for making your equipment, and all the personnel that was building your equipment. So it's not easy to redo again back something with a gap of 2 years. And there's a lot of interference. And when you build the technical infrastructure, if you build it only for feeding a machine that is 10 times smaller than the future one, you have not designed the good components. So it's not so easy to extend a machine. Same thing happened for ELC. Technologically great machines, with no doubt are fantastic fixed factories, but implies a lot of, I will say, courage, because if you do it, and again, it's my personal opinion, then you have to do the final one. It will be very difficult to pass from the small version to the big version. And if I will be in LLC, I will lie again. I will say that I can do from the small to the big one, but technically it's really complicated. And unless you design all the technical infrastructure already for the bigger version, and that implies a lot of cost, because again, technical infrastructure is nearly as expensive as the machine. If I go back to Halloumi, people forget that cryogenics is 1/10 of the cost of the project. That civil engineering is nearly 2/10 of the cost of the project. So if you accumulate all these infrastructures, you will see that is eating half of the machine. So muon colliders. I know that a lot of people, and I think I arrived in '96, and already I listened about muon colliders. I think even before in '95 when I started, and they are incredible machines. And I will dream of having a muon collider. But today, still, we have a lot of even more than technical difficulties to making one. And I would dream that there's a courageous team that really dedicates themselves to make a muon collider, because it will be like the jewel, everything in one. As happened with Click and ELC, they have tried to find as much synergies as possible, because this is not a way when you have little resources to advance faster and to aggregate communities. Will work. I hope this is how the states they wanted to make a muon collider, and the first layout that they created in Fermilab. I have seen the equivalent one in CERN, and Carlo Rubbia is really pushing for it, and it's a dream machine. But today we need a complete change of paradigm to make it work, but it will be a dream machine. And finally, my last slide, plasma accelerators. Again, a beautiful technology. I have put the reference of a full Zen accelerator school dedicated to plasma acceleration, but today is a concept. So it works, awake demonstrated works, but clearly it's not for high energy physics. But I will make a joke. It's like the web, an interesting concept. And sometimes the interesting concepts become a reality and becomes a change in your life. So again, clearly, and in that sense, our Director General has put funding for the muon collider, has put funds for the plasma accelerators, even in the moments where we are cutting everywhere, because we have to continue with all these other technologies that can change completely the paradigm of the accelerators. This was my last slide. I hope I have, probably you haven't learned too much, but I hope I have created the interest to go for the next slide, that is more reading, where you will see a lot of reference of documents that will enlarge your knowledge. I, of course, recommend you, there you have a lot of books that will again, learn you about the history of accelerators, the component of accelerators, the evolution of them, the usage of them, but you have also all the links to the reports of the future colliders and the linear and circular, so that you can again have a full impression of what is required, what is needed. And again, more information on other concrete things, and two really important links. One is to the CERN Accelerator School, where you will see that in my slides, you have all reference for all the chapters in the different components, for example, of the machine, that will you open to a complete new world that cannot be seen in just 2 hours. But I really recommend you if you are interested. And I think that's all.
Thank you.
Thank you very much for your attention, even if I'm afraid I'm here far away from you. And I know that the sun is...
It would have been nice if you were here, but okay. This situation is like this. Yeah. So any question? Yeah, just...
Hello, am I audible? So Isabel, I have this question. Hello, am I audible? Okay. So my question is that technology is improving day by day for both magnets and energy delivery systems. But there has been a while since we had a last breakthrough in our technology. So if do you envision some breakthrough which may lead to compactification of our high-end heavy-end colliders or linear colliders in the future?
Well, I will answer you in a historical view. Okay. Today we are using for the new triplets neobill-13. And neobill-13 was a technology that was discovered in the 70s and used in the 70s, and the first magnets were done already in the 70s, and was not anymore used because the first magnets demonstrated was a too hard to use technology. So some of the technologies that today we think is innovative come really from 50 years ago. But sometimes we retake back thinking that there are some progress that have been done that will allow to make it more simple. For example, we tried to make new cables with 2 different technologies, but none of them have behaved as we have expected. There's new superconductors that exist, new, since again, all ones that we can try again, but we have to make, since I don't know, you have passed really the concept that you need a lot of R&D to make something work, and that there's no dead path until you have really tested it. Sincerely, I think that we have to go for higher temperature superconductor. But today, our real limit is the tapes. So it's normally all the machines that we are doing is with cables, and we have always making coils and with magnesium diboride. Today for the magnets, we are using tapes of magnesium diboride. So we are not still managing the technology. But I think, and I hope that the new breakthrough comes from these highest temperature superconductors. This will be the moment that we are able to make magnets in a repetitive way using this kind of technology, probably having a change on how we are using today the material will make really this change. But let's say that there's a lot of work still to be done. There's people more optimistic than me, but today we don't have anything that makes us really fully believe that it's the way. I don't know if I'm clear. Since we are trying a lot of technologies, we are trying also to remember this part of industrialization, so making it work in industry. We are working in parallel in a lot of technologies, but none looks like the winning horse. But again, it's a question of work. I remember the first test of the magnets. That was not a problem of the superconductor, it was a problem of design. We were designing with aluminum colors that were impossible to produce with the same shape all the time. So we have a pre-compression, it was not working. Then we had this gap that was opening, and then the coils were moving, and we solved it in just 1 year, changing the material on the colors. So sometimes you think that you are in a dead end, and then the light comes. So it's hard work, and continue trying until we manage.
Thank you.
Any more questions? If not, thanks, Isabel.
It was my pleasure.
Okay, thanks. Yeah, now before lunch, I have this. Okay, this is just to the student and the school organization matters. Sometimes today afternoon, I will give you this. As I said, the Saturday we will have a 16 group will present their experiment, and I ask for this all these instructors to give the name of the people. Based on that, we'll choose the 16 groups. And okay, my request is that don't spend much time to prepare your preparations and the slides. You attend these lectures and others. This is the one thing. And second thing is, I will today or tomorrow I will give you the feedback form. Basically, all the classes, lab sessions, and overall organization of the schools. Please fill this form. That will help us for the future school organizations. Okay. Okay. Then now go for lunch and then experiment. One small thing. Today also at 6 o'clock onwards, that you go to the different lab which was not assigned to you. And after your regular lab sessions. Okay.